Here it is. All right, so yeah, let's get our bearings on this one. So this is the one where we had this, and let's kind of talk about how to set this up. There's a good trick you can use here with physics. We want to always, and we do this in calculus a lot. If we can come up with an equivalent problem that's easier to deal with, that's going to give us the same answer, let's just do that. Right. So there's not a huge change we're going to make here, but we've got this. They give us the mass of the truck, and they're wanting to know. Let's see, what are they telling us here? They want to know how much total weight can it tow up the hill in pounds. That's kind of. But there's all it is, honestly. We can just do a real simple changer. And I'll tell you, I think it's 2.2 pounds per kilogram. But we can look it up. I mean, you can just look it up on your phone, what the conversion is. Like, what's the weight of a kilogram on Earth? So let's just assume that the truck is massless, and we're going to pull everything is. We're going to look at the combined load, right, and see what that is, and then we'll just subtract away the weight of the truck. Sound good? Okay. All right, so they tell us the radius of the tires. We're going to want that in meters, right? They tell us the torque, maximum torque that the truck can exert on the rear axle, which is ridiculous. It could never handle that. And then we want to know if it's going up this kind of an angle, what's the most weight it can pull? Okay, well, what can we do with this torque measurement? If we know the radius of the tires and the torque, what does that tell us? What's our torque? Where's our torque relationship? Right up here, right? Sure. So what's the length of the lever arm here? 41.3. Yeah. Okay. It's just going to be the radius of the tire, right? And remember, you just think of a tire as being a bunch of spokes, which are levers with just little rubber pads on the end, right? That's pushing the car up the hill. Okay, so we're able to pretty easily figure out what F is then. If torque equals force times lever arm, then force must just equal torque divided by lever arm, right? So we can do that. That's no big deal. So we know then that the force that we can apply equals torque divided by lever arm. Both of those things we know, right? Okay. Now what? Really, once we know that, this isn't too terribly bad.
Start filling in all the different thing you do.
So
weight and the normal force and the
okay,
torque and the...
right. And if we look at the free body diagram, we're assuming that there's no friction, right? I mean, there's friction, there's rolling friction, but that's not really causing that we're not having to overcome that, right? We're just turning the tires and that's moving us up the hill. There's no other, we're going to ignore all other friction. And there would be friction. There'd be internal friction inside the truck. There'd be some friction in the axles and things, but we're just ignoring all that. So if we know what the force is, we can calculate it. It's just going to be that huge number divided by that in meters, right? And let's go ahead and just get a number on that. If I pull up the calculator, let's see what we get. So we get 174,550 Newton meters divided by 0.4103 meters. If I turn centimeters into meters. So we get a pretty big number, right? So we're getting 425,000 newtons of force. That's a lot. Think it could? Yeah, that'd be nice. Okay. So then all we've got to do is just figure out if that's how much force it can apply, what kind of load would that mean if we're pushing it up an incline, right? So if this is the combined weight of the truck and the load, and we're going to end up solving for M. We don't know what that is yet, right? There's the combined load, and the only forces acting are gravity and what else? Normal force. That's it, because we're ignoring friction, right? Okay, and we're gonna go ahead and look at this in terms of a parallel and perpendicular component, right? Does that make sense? So then, if we set up equations of motion here, this is what we're gonna call the positive parallel direction, and that's what we'll call the positive perpendicular direction, right? Okay, this is the part I wanna make sure everybody's getting to the point where they can kind of see how to turn this into equations of motion, right? So if we write an orthogonalized free body diagram, we're just gonna put the components on there with our chosen directions. Because really all we care about here, right, is how much, how much force is being generated up the hill and how much is being generated perpendicular to the hill, right? Okay, so then we end up with, if we do that, here's our object, there's the truck and the load, right? Everything combined. And we've got normal force, we've got the perpendicular component of gravity. Well, what's that gonna be? If this is theta, then which of these angles, that one or that one, is theta? Top one's gonna be, right? Yeah. So that's theta. So then in terms of theta, what's that gonna be? It's gonna be a cosine issue, isn't it? The perpendicular component is gonna be mg times the cosine of theta. And then this guy, if we move him up there, he's gonna be pointing down in that direction, and that's mg sine theta, right? Does that make sense? Okay. So then that's gonna be the amount that we can, the amount of force that we can overcome, right? Does that make sense? That's gonna be the way, if we're gonna move this thing up, I guess one way we can maybe look at this then is, that's the amount of force that's the gravitational component of the load, truck plus the trailer, that's pushing down the hill. So what are we gonna have to be able to apply? Well, I guess we could add one more force here, couldn't we? We could say, okay, well then, this is gonna be our, call it driving force, right? That's the force that the truck has to be able to apply to overcome that, right? Okay, so what's gonna be then, let's call this equation 1. And this is gonna be the one that's gonna involve the perpendicular components. What's the net perpendicular force here? Okay, normal force, good, so we got normal force minus mg sine theta, okay. No, you're right, oh, mg cosine theta, sorry, you're right. Equals 0, there it is. This time, is that really of any use to us? Well, not so much, because we don't really have a friction this time, do we? Right? So we don't even really need it. All we really need is the other equation. We just want the one that's going to be parallel to the surface. That's really the only one we need. So what's going to be the net, if we were saying up the hill is the positive direction, let's just say that, right? So then what's going to be, I guess I got to add this guy, don't I? There's our driving force. Right, pushing up the hill, there's the weight pulling us down the hill. So what's going to be the net force acting parallel to the hill? Okay, which one? We said that's positive. So that's supposed to be a D. So driving force minus mg sine theta, right? Now, what is the net force always going to equal? Mass times acceleration. Okay, now let's talk about that. So, if we want to pull the maximum possible load, that's going to be the load where we can't accelerate anymore, right? We're just going to be able to just keep it moving at constant speed. If I can still accelerate, then I could have pulled a little bit more. Agreed? Yeah.
If you were not moving, like you started out not moving, would you be able to move at all since you're not able to accelerate?
Right, so you wouldn't be able to, would you? Right, so let's just make the assumption here that we've kind of towed this thing along the ground and now we're just going to be able to just keep it at that speed, right? So it's going to be when the acceleration equals 0 is when we're going to be topping out. So this really isn't so bad then, right? What do we end up with as our equation?
Driving force equals mg sine theta.
Yeah, and we know what we're really trying to find here is the mass of the load we can pull up the hill, right? Everybody agree? Well, because we calculated what our maximum driving force was, that's just gonna be the torque, right? That the car can generate, the engine can generate at the axle, divided by the radius of the tire, right? That tells us the maximum driving force, so that is F sub D. Okay, so all we've got to do then is solve this equation that we get. We get the equation you just told me, mg sine theta equals driving force, right? Well, we know theta, that's 21.7. We just calculated F sub D, and we know G, right? So then all we'd have to do, M is just going to equal driving force divided by G sine theta, right? So let's see what we can do. There we go. Okay, so once again, what do we got? I got to look up and see what those numbers are. So driving force is that number, right? Divided by the quantity 9.8 times sine of 21.7. Gives us a pretty big number. That's the number of kilograms, right? That we can tow up the hill. Make sure am I in degrees mode? Yes, I am.
You have to change it to pounds.
We have to change it to pounds. Right, so that's the total mass that we can pull up the hill. So now what are we going to do here? So we've got our truck has a mass of 3,050 kilograms. So what am I going to have to do to my answer then? I'm going to subtract that. And that makes sense because I'm subtracting apples and apples here, right? Not apples and oranges. I've got kilograms. I have the mass of my truck. And here's the maximum mass that I can tow up the hill, right? So I'll subtract 3,050 kilograms from 117,000 blah, blah, blah kilograms, right? So that leaves us with, oops. Still, that's really a big number, right? So now all we've got to do is just figure out what the weight of that is in pounds, right? Technically, what we should do is turn that into newtons and then convert newtons to pounds. Okay, because this is, and let me point something out that's kind of important here. Remind you of something we talked about a long time ago. Are pounds and kilograms equivalent units? They're not really, right? Remember, kilograms measure mass. Mass is a different quantity than weight. Weight is a force, mass is not, right? However, we do things like this all the time. If you go into a weight room and you put on a 45-pound plate, that would be the equivalent of how many kilograms? 22.5, right? So how do we do, well, what are we saying there? We're saying, okay, I get it. Kilograms and pounds aren't the same kinds of units, but everybody that's lifting weights is going to be lifting weights on Earth, presumably. And on Earth, where G is relatively constant, it's a pseudo-constant, it varies by extremely minute amounts, then we can just assume always that we're talking about the weight of those kilograms, right? The weight of that mass on Earth. And so then there is a conversion we could do. Technically, what we should do, though, is convert this mass into a standard, an SI weight, which would be newtons, and then convert newtons to pounds, right? See what I'm saying? And, well, why not? I mean, why don't we just go ahead and do that? Because all I have to do is multiply by 9.8, right? If this is the mass in kilograms, if I multiply by 9.8, everybody agree that's going to be, that's a lot. That's, what is that? That's over 1 million newtons, okay? Now I want to convert newtons into pounds. Well, let's Google that. Yeah, it's all true. I do. So let's see here. If I go about, so what are we doing? Newtons to pounds? What's our conversion? 0.224809. So we're just going to does that make sense? If we want to go from newtons to pounds, we got to multiply by that amount, which makes sense because pounds are bigger units than newtons, right? So we'll just multiply by 0.224809, and that gives us still a pretty big number, right? So what kind of load could we pull up there? How many places are we rounding this thing to? I forget. It's I think it's maybe more than that.
Well,
We got 5 there. Oh, that's right. There's 4. There's 3. Yep, you're right. It's only 3. Yep. So we get what? 252,000.
I got a difference of like 400 pounds almost between just like converting kilograms to pounds and kilograms.
That's still not going to probably impact our answer. But the reason you did is, what do you use for your conversion?
So from kilograms to pounds, I multiplied it by 2.20462.
Wow, I wouldn't think it'd be that much then. One of our conversions had to have been wrong, because there's no way it should have been 400 out of. That doesn't seem right.
That's what I did. Yeah.
Well, I'll tell you what, we'll calculate it both ways. We'll see what we get. So we'll see how different mine is. So that was our answer, wasn't it? No.
No, the next one.
That's our answer in kilograms, right? Times, let's go back to Google and see what,
Oh, so there's more to it?
No, he's just doing it different. But he just do this.
75 difference.
and now we're doing kilograms to pounds.
No, did not do it. Oh, oh, I think you're talking about.
That's supposed to be.
When you have to divide by 100.
Yeah, that's right.
That's right. 2.20462.
2.20462. Okay, so I'm going to multiply that one because I'm going from kilograms to pounds.
Yeah.
So times 2.20462 gives me.
That's the difference by 3.
I get it's less than that. It's a difference of less than 200.
Well, you just have to round it up, right? 3. So
Yeah, I mean it's not going to affect the rounding. That's really so. One of those is not a very good conversion factor. I don't know which one it is. I don't know my conversion factors that well, but one of those is bogus because they both were about to the same. 1, 2, 3, 4, 5. That's to 6 sig figs. That's to 6 sig figs. So one of those is not very good. Google messed up. I don't know which one it is. Yeah, but that's the only possible answer. I mean, they've been rounded. Presumably, they've been rounded. But look at it this way. I mean, here's how I would look at this. You're going out to 1, 2, 3, 4, 5, 6. So you're going to go out to essentially to 7 decimals before you have a difference, right? 7 decimals, multiplying this by something out to 7 decimals is not going to account for that much of a difference.
Is pound force the same as pound?
Yeah.
Okay.
Yeah, I don't know. One of them's not right. But either way, our answer ends up being the same thing, which is
You don't have to put any.
252,000, and then the pounds are already there, so that's all I would put. Right. Now, is this the same one? Oh, this isn't the same problem, though, is it? No, it's not. That's a different problem. So how realistic is that? Probably not. I mean, you guys be the judge. You think your trucks could pull, how many tons would that be? Divide that by 2,000 pounds. You think your truck could pull 126 tons up a hill at a 21 degree angle?
Oh, yeah.
So it's probably not that realistic. That's kind of a lot to pull.
I was off by like just.
The nickname BMCC was already took on.
See, that seems about right. That seems pretty small.
That's well.
It's just an ad.
Here, check it out. That seems, here, I'll tell you what, we'll just do this one real quick.
Oh, you're right.
We'll just check this one. So this one would have been, the force would have been on this guy. We can like recreate this, right? So the force for this one, come on, would be 241, the torque, 241,830 divided by 0.4084. So that's going to be the force. And then really all we've got to do, right, the math's going to be all the same. The math is we're just going to divide the driving force by g sine theta, right? So,
Okay. So
right.
what if the difference of mine does matter for rounding?
It does matter?
It does matter.
I'd use the newtons to pounds. Okay, so I'm going to divide that by the quantity g times sine 27. And I get that. I got to assess the mass. I got to subtract away 2740. And then I'm going to multiply by 9.8. There's my answer in newtons. And then newtons to pounds, I'm going to multiply that by 0.22489. And I get that. Okay, so rounded to 3 sig figs, that was the angle, right? I'm going to get, oh darn it, come on. I'm going to get 287,000. Okay, so that's right. Okay. Everybody see that? That's kind of a tough one. Yeah.
Wasn't that bad.
I don't mind giving you hard ones on the problem sets because they're worth 10% of your grade. You know, I don't feel as bad about it on there.
Hey, you can't build a problem set if you never do it.
That's one way to look at it, I guess. Yeah.
Which is why they should be worth 5% of our grade.
Okay.
It's different. It's different. No, it's different. It's still filled up.
All right. So now what I'd like to do, let's have a little look here at, we'll do our test review.